Welcome! Today we're learning complex topics in a simple way. We're doing frontline reinforcement learning, hands-on in the trenches. By the end of this video, you'll know Dreamer, how it works, its architecture, and the code for it. Does that sound good? Because you're here, I assume that you roughly know what Dreamer is. Either way, I made a video about it. That's like a non-technical overview, the idea, the concepts behind it. I showed there how dreams look, how reconstruction looks, so it's kinda cool. But as a quick summary, Dreamer is one of the best reinforcement learning algorithms, and it uses a world model. So classic reinforcement learning plays the game to learn the behavior, but Dreamer plays the game to learn the world model, to understand what's happening, how the world works, and based on this model, it learns the behavior. So it's slightly more complex, but it's much more complex, but no worries, because I'm here for you. I wrote my own implementation of it, which you'll appreciate the clarity of. But that's later, forget about the code for now. First, we have to learn the architecture. We're starting with the publication and their diagrams. Then we'll get to my diagrams, which are much better, of course, because otherwise I wouldn't make them. And then we'll get to the code. Is that clear, my students? Any questions? Good. Let's begin. So here we are, mastering diverse domains through world models. And first of all, you cannot be afraid of publications. You cannot be afraid of reading the papers. They are written by the people, for the people. But the people aren't always willing to read them. We're lucky that this paper is actually pretty approachable. Like, look at the language. It's not too complicated, it's very pleasant. Plus, it's only 11 pages. The rest are just like references and additions. So it's quite short. But okay, let's read the abstract together. They write, even though there exists some specific solutions, creating a general universal algorithm has been a fundamental challenge. So we present DreamerV3, which on one configuration solves over 150 tasks and got diamonds in Minecraft. That's it. It was that easy. In my video, I showed you that the diamonds in Minecraft are kind of cheated, but let's give him that. That's fine. They brag about the performance, of course, much better. PPO, you should know this if you're learning reinforcement learning. DQN, you should know this. mu0, you should know at least conceptually, but that's beyond the point. They brag about the performance, okay? Then we get to the introduction, and the introduction is just a longer version of the abstract. Like, I recommend you watch it if you're interested, for the background, for the vibes, for the like industry info, but it's really nothing new. We go further, and this is what we care about. We want to study the architecture, training process of Dreamer. And remember 3 steps to training Dreamer. Gather data. Based on this data, train the world model. And based on this model, train the behavior. Okay? Okay, now let's read this. Let's see what they wrote here. What can we read from this? The world model encodes sensory inputs into discrete representations Z. So here encoder encodes into Z, that are predicted by a sequence model with recurrent state H. So this discrete representation is also created by the sequence model, given actions A. Hold on a second, okay? They show that this takes action, but it's not just action. The diagram shows that it also takes previous recurrent state and previous discrete representation. That starts to show you that the diagram is a bit too imprecise, but let's go further. The inputs are reconstructed to shape the representations. So like this is justification of existence of the decoder, but I'll explain it later, okay? Don't worry about it. Don't worry if you understand nothing from this. The actor and critic predict actions A and values V and learn from trajectories of abstract representations predicted by the world model. So this is this whole part in one sentence. I'm not going to analyze this diagram. I'm just going to reference it later as we go on because, you know, learning from this is not a great idea. What's better is when we go down, here we have more details of the world model. Here we have every neural net listed with inputs and outputs. So that's much more precise. That's much better. Okay, let's go through this. So we have the sequence model that takes in previous recurrent state, previous discrete representation, and previous action. Okay, this matches our diagram here. And it outputs the recurrent state. Okay, the encoder takes in a recurrent state and observation to produce the discrete representation. Dynamics predictor takes in recurrent state and outputs discrete representation hat, z hat. Okay. Like, I don't feel like they explain in the paper why does it look like this? Why do you predict the same thing both ways? I'll explain it, but like, I'm just like curious. Like, I wouldn't understand it if I didn't read the code. But it's fine. A reward predictor predicts rewards based on recurrent state and discrete representation. And the same inputs, continue predictor and decoder. This, they mark it as recurrent state space model, but like, it doesn't matter. It doesn't make us any difference. Like, I consider all these nets the world model that we're training in this step here. And as you probably noticed, the dynamics predictor is like a new thing that exists like between these layers here. Here's a sequence model. Here should be dynamics predictor that creates this representation. Plus also encoder and decoder use the recurrent state. And they don't show it on the diagram. Why? Okay. Also, they show you like two types of observations here, which is image observation and just vector numerical observation. In practice, we use either one of those. It could be both, but it's usually one of those. So let's just focus on images, okay? Reading the whole paper, as I was first learning it, I read the thing, analyzed this, and I wanted to make my own better diagram. And I made this, which much better fits the publication. This is just me studying it and creating the most faithful representation, the most faithful diagram that I could make. So let's study this for now. Later, we'll get a better diagram that I made based on like my code and I changed some names. It'll be better. But for now, let's study this because we're trying to understand the publication. Okay? We're starting with image observation. We pass it to the encoder alongside the recurrent state, right? To the encoder to create discrete representation. But here we have a sequence model with recurrent state that we pass to the dynamics predictor that creates the same representation. I mean z hat this time. And question number one, before we go further, is why is this discrete? First of all, this is one hot encoded matrix, meaning only one value in a row can be 1. The rest are zeros. There are all zeros here. And the matrix is 32 by 32. It's variable, but they used in the publication 32 by 32. But why is it discrete? Why is it like this? Why not just have like a bunch of numbers and values here? For the answer, I recommend Edan Meyer's video. Actually, the last video he made 7 months ago. I mean, the title is kind of mysterious, doesn't tell you anything, but look at the thumbnail. Do you recognize the diagram? Right, so he made a video. I mean, he studied this. He exactly answers why is it discrete, which, long story short, it performs better, but why is it like this and what's happening? Why did they use this? It's a great video. Let's just say that discrete is for better performance. Question number 2 is, why do we predict this both ways, from the dynamics predictor and from the encoder? Okay, and it's because we want to learn the behavior. Let's look at the diagram. We want to learn the behavior without access to the observations. So for the world model to know what's happening, to create the rollout, to have step by step what's happening without actual access to the game, we need the dynamics predictor here. And encoder is only the guide for the dynamics predictor. So we create the encoded representation, this representation, and it's a guide for dynamics predictor, because dynamics predictor has access to recurrent state only. Encoder has the same recurrent state plus the observation, the actual observation. So encoder here is better informed. The representation it will create will be better informed. It will be a better representation, but it's a guide for dynamics predictor, so we can do the rollout. We can learn the behavior without using the encoder at all, because we will not have observations. Okay, so I'm in a complete mess here, but these two nets are like cooperating. They need too much. This is student, this is teacher, okay? But it will be even clearer later on. And one more thing, recurrent state, I think of it that it encodes the past. So encoder, based on the past and based on what we currently see, represent the present. But dynamics predictor is just like, based on the past, figure out what's the present state. I hope that it's somewhat clear so far. We'll reiterate on this in a future diagram. The whole pipeline will repeat the whole thing, so no worry. But for now, we have the discrete representation that we take alongside a recurrent state, and this is a full representation of the state of the world. I call it later full state, because this is like the past, all the time data, what happened recently, and what's the present state. That's why, based on this together, reward predictor and continue predictor predict, what's happening, what's the reward, what's the continue value, meaning like, did the episode end or not, and what's the chance for it. And then we get the decoder, okay? That reconstruct, that based on this compressed representation, this full state, tries to reconstruct what it saw originally. The question is, why the decoder? Why do we need it? Because I will tell you right away that we don't use the reconstruction to anything. Like, it's not useful like directly to us. Like, I made a video for it, I made visualizations to like show you how well it works, but it's not like practical directly, because rewards, we need rewards to learn in the imagination what happens. Continue also, but this is not needed because actor makes decisions based on the full state. So what's happening here? In the paper they wrote a mysterious sentence that the inputs are reconstructed to shape the representations. And this justifies the existence of the decoder. Okay, think of it like this. The observation is compressed to this discrete representation and this recurrent state. So the whole state of the world is compressed, vastly compressed. And this compression can go too far. And the decoder applies pressure on the whole system to be able to reconstruct the original observation you know, with some losses, of course, but to be able to reconstruct it based on these representations. That's why they use the decoder to shape the representations, so they're more informative. And apparently the pressure from reward predictor and continue predictor is not enough, because like apparently these representations need to convey something useful for the reward predictor to work well. But apparently it wasn't enough. I don't know, it's kind of an interesting test to run, what happens if you delete the decoder, but they use it, so we use it. And then we go to the next time step. Here the recurrent state was initialized because there is no past. There was not like nothing to convey in this recurrent state. But here we already feeded the previous full state, the action. We have new recurrent state, new representation, new observation, because we kind of like go to the sequence of our collected experiences, and it goes on and on. I hope it's getting pretty clear by now how the whole thing works, but this was based on the publication. I studied the publication here. But next diagram is my improved diagram that's based on my code with slightly changed vocab, so you will have to get used to it, but it's really much better. If you understand my next diagram, you'll have much better time understanding the code. Also, this diagram introduces the behavior learning that we're missing here, but it'll be really easy after you understand the word model training. Alrighty, welcome after a small break. I know that we're going to like the same thing over and over, but there are always some changes, and also I'm not sure what pace to have, right? Like, it's my first tutorial. Like, all of this is extremely easy for me because I spent like months on this, okay? But for you, like, I don't know, I'm trying to be thorough with the knowledge I convey. So, you know, every feedback is welcome for the future. But okay, let's get to the diagram, and you can already see the change is being made. Hopefully, I color-coded the variables and nets in different colors. First of all, this is an important change, that we split the encoder from previous diagrams into two separate nets. I was analyzing other implementations and they always do it like this. And I personally also like this way of doing things because encoder becomes like the choke point, the processing block between observations and like representation of this observation, kind of, that's universal. Because observation can have many different forms. It can be vector values, it can be image. Maybe you can do something crazy and connect many types of different observations and somehow process them. So this is like a point where we process the observation and standardize the form, okay? Because in encoded observation, I can set like a constant value, like whatever the size of this is, I can have a constant value here. It's always like compatible with the input here. So I just like the split. We'll be doing it like this from now on. And thanks to the setup, we can have a separate name for this net here that produces then this representation. So I called it posterior net because it's the network that creates the posterior representation. Go with me for now. And we can call this prior net. And it has like from the name itself, you can figure out that these two nets are connected, that this is prior, this is what we think the state is without seeing the actual observation, and this is posterior, this is our like additionally informed belief about the current state. So we have two different nets, prior net and posterior net, that produce two different variables, prior and posterior. I also indexed it with 0. And these two things we call latent states. This is a latent state and this is a latent state. People will call it, like in other implementations, they will call this these two stochastic. And this is deterministic. Recurrent state is deterministic. And it's just like I get where the naming comes from, because this is like the past is determined and the present representation is like probability based because it comes from the distribution, but that's not what I want to focus on while naming the variables. So I will always call this recurrent state that encodes the past, and the present representation is the latent state. Latent state is when I like don't distinguish which exactly version it is. Just latent state is the discrete representation. This is the latent state, the one hot encoded vector. And I also used 16 by 16, but it doesn't matter because we can freely modify the sizes. So latent state, this is a latent state in two versions that come from two different directions. And recurrent state comes from recurrent model, but this is then because like we initialize it to all zeros. So it's not processed by the model, by this network. Like I just initialize it like in the loop. So it doesn't really come from the model, but later it will come from the model. Okay. And we create the full state by concatenating recurrent state and latent state. But in this diagram, it's also explicit that we use posterior for this. Posterior because it's the more informed, more accurate latent state, right? So we can more accurately train all these nets. Okay. So we create a full state, we pass it to the nets, a reward continue in the decoder, right? And this full state alongside an action goes to the recurrent model to create the loop again and continue the process. And here I have a note, because it's important, that action comes from the buffer, full state comes from the posterior. It's important for you to remember this, that action here comes from the buffer, because we train the word model by replaying sequences of what happened, of what actually happened. So we can match our predictions to what actually happened. Because in behavior learning, we'll have a recurrent model that takes live action from the actor and full state creating with the prior. Okay, but that's foreshadowing. Don't worry about it for now. So we were at this time step. To create recurrent state 1, we take full state 0 and action 0, right? Prior 1, posterior 1, observation 1, full state 1, reward 1, continue 1, reconstruction 1. And then the cycle continues. And it goes until it reaches batch length steps. So we predetermine, it's a parameter, how long the sequences we train on. So this is how the word model training goes. We instruct, we pressure, we order the prior net to match the posterior, and we order all these nets to match what happened in reality when we were playing the game, right? And encoder is trained just like indirectly, like we back propagate through like all these nets, so the encoder produces useful representations. Now we passed the sequences. I mean, this is just an example of one sequence, but there are like multiple sequences in parallel. Doesn't matter. Like we iterated on the word model. Now it's time to advance to behavior learning, to actor-critic training. You see the lines here. This is how we advance to the next step, because you remember the diagram from here. We begin actor-critic learning, that's also called behavior learning, with one observation that's encoded, and then we imagine just in this latent representation without access to the game. Okay, that's how it's done. That this full state is fully grounded because it's created using the posterior, well-informed posterior. And this well-informed full state is passed on further as an initial step for the imagination rollout, right? I don't have to encode it again. I don't need new observation. I can just connect the dots. Like I have already this representation here. I don't need to encode it again. Like these two are not separate. I just nicely connected because full state is already a full state. I don't need observation. Okay, so we pass the full states further. In my current code, I pass every full state in theory, I believe you could just sample a specified number of these full states from all these sequences, but for now I pass all the full states and we go further. I color coded the nets differently to distinguish it. Oh, I even wrote it here, that this recurrent net is like the same net that's here, but it's not being trained at the moment. It's constant, right? We only train actor and critic here in this step. So I just changed some colors. We have the well-informed full state here that's passed to the actor, because like this is actually like a new observation. It's encoded, but it's full observation, full state. So like every net operates on this full state. That's why I cared about connecting it to one concept instead of having like recurrent and latent state separately. So we have the well-informed full state that's passed to the actor to create an action, and the same full state is passed to the recurrent model along with that action to create the recurrent state in imagination this time, right? So this recurrent state can be passed on to prior net that's trained like using the posterior, but now we have no posterior. Now we have just the prior, and this recurrent state and this prior come together to form a full state, yellow this time because this was from the posterior, this was well informed, but this is just our imagination, full state. And this fully imagined full state is passed to the actor to get an action, to the critic to get the value, to the reward model, to the continue model. And they are not being trained. They are guides to actor and critic, okay? They are guides. And this action goes along with the full state to the recurrent model. And we're in the same spot that I mentioned earlier, that this is recurrent model, but it takes live action from the actor and full state from prior. While it used to take action from the buffer and a full state using posterior, right? Do the dots connect in your head? Please say yes. So we have a new recurrent state, new prior, new full state, new actions, new rewards, new recurrent state, new prior. This was like the pinnacle of what I was trying to teach you. Oh, I even forgot, because like here we don't use the decoder. I mean, I wrote it here because we don't use the decoder unless you want to show your audience how the dreams look, okay? But here the decoder is not traditionally used. I use it just like for fun visualizations, but it's pretty much non-existent here. And then continue until it reaches imagination horizon steps. That in practice, both the Dreamer and I use 15, okay? Now, this was one rollout, one trajectory, but from every full state, from the word model training, for every initial state here, we create separate rollout, right? And that's the whole training pipeline. Let that sink in. And that's the end of our theory here. How does this diagram look now, huh? It was like too vague at best and misleading at worst, okay? That we got settled. Then we scroll down and then we get to the details, to concrete losses, to tricks, like 1% uniform mix. That I will be showing you in the code already. All the losses here, the equations, this is lambda values calculation, actor critic, okay, advantage maximization, plus entropy term, simlog and simx, okay, too hot. Oh no. That hurts because this actually doesn't work yet in my implementation, but it's not necessary. It's just like a small thing, but kind of annoying. I wrote it correctly, everything's fine. It's just it just doesn't perform well. Like, what do I tell you? Some more results. Yeah. And then it's just that. Alrighty. Oh my goodness. Are you ready for the code? Brace yourself. But before we get to the code, I wanted to start with this Reddit post. DreamerV3 code is so hard to read because it really well sums up my experience and many other people. He spent 3 months trying to understand the paper and the code, and after 3 months, he's still overwhelmed. I mean, he was still overwhelmed and didn't know what to do. And you have to trust me that this code is really, this is the original Dreamer code, and it's really complex. They support so many different like frameworks and ways of doing things. Like here, I remember that they, like for saving the metrics, they support JSON-L, whatever that is, TensorBoard, and that's like industry standard, expa, 1db, scope. And like this is the main script. Like, can you understand easily what's happening here? There's so much code, and I have a good example for you to illustrate this well. This is, for example, how critic is trained from the paper. Like, before we get into much detail, but just know that we minimize, this is the loss, we minimize this, so we maximize the probability of returning lambda values based on the state. Okay, and lambda values are calculated like this, with this one equation, where we take into account rewards, continues, current evaluation from the critic, and lambda return from the next step. So to get the lambda return of this step, we can like reference the next value and the next and the next. So pretty much the way to calculate it is to start from the very end, because the final value is given, that is just evaluation of the critic, and then we work backwards on this equation. And let's look at functions that implement this lambda return, this equation. This is original Dreamer code, like okay, they do something here. The indexes are quite complex. I need to spend some time on it. Then they iterate backwards, then reverse the list again. The variable names aren't even like full words. Like, how much would it cost them to call this reward? And we have to use the bootstrap. So like the bootstrap is the last value, the reference value, and the bootstrap shifts constantly with each step. But why do we have last and bootstrap, and this is what? Oh, discount. Like, this is quite unnecessarily complicated. Let's look at sheeperl version. This is a nice library. I studied their code a lot, but let's look at their version. It's the same thing with reverse list. We reverse again, we stack, no, we don't stack it, we concatenate it. And they calculate the intermediate values. Why? It's like, yeah, this can be done like in advance without the list, but like, I don't know why. I don't know if it's quicker than my code that I will show you in a second. Then Simple Dreamer, they adjust indexes here. They do the same thing. They stack, reversed again. Okay, fine. But then look at my code. I don't believe my code is slower, if it's slower at all. But it's, most importantly, so much cleaner. Like, I don't need to pass the device. I don't need it. I just like infer the device from rewards. I don't need to pass in horizon length. It's inferred based on the reward shape. I create the buffer for lambda values, set the bootstrap at the beginning to the last value, then go in reverse, calculate the equation. Just, this is the same equation perfectly. So you can easily understand it and see how it works. Then we change the bootstrap. And it works perfectly. Why? Yeah. Okay, so now you understand how roughly how like what was the idea behind my code, what was the approach, and I was pretty much inspired by this because I was trying to learn it. I was just like, wait, I can do it so much cleaner and help so many other people. So that's what I did. Let's close this. Let's see my actual code. Natural Dreamer. I called it Natural Dreamer because I want to emphasize that my Dreamer is like a natural. Like he shows up, he doesn't really fit. I wanted to call him Underdog Dreamer or Amateur Dreamer because he's not a professional. I mean, wait, all these implementations are just like serious teams. We're academics. We want to have performance. We like do stuff. I show up. I just studied it. I don't know. I'm not in the industry even. I just like came here. I wrote Clean Dreamer because it's this is what I do. And this is how I think. And this is pretty much, these are pretty much other dreamers. They use super macro lenses for anti-polarizing, anti-reflective, laser microscopy, telescopy zoom. My dreamer shows up and is just like, I don't know, I shoot. Like I try to hit the middle, things like this. Like this is natural dreamer. So you can check it out, you can start it, I dare you. But let's get to the code now. Let's analyze the code. I'll show you my local version that I have here. This is the main script. Okay, I already started making some changes, so I'll quickly stash it so we don't have any changes, because I forgot to mention that I made it nice for you because there was a whole mess with many different versions. I had some attempts, had some failures, different repos. So I just put it nicely for you that this tutorial is made on my first commit. So if you want to have the same code, the exact same code, just go to the first commit of this repo, okay? And then you can trace back the history. What did I change? I already have I already see things to change. I already have some changes in mind. I can make endless changes. Whenever I go to the code, I see wait, this can be done better. So this will change for sure. I need to add more features. For now, only one environment is beaten, and car racing. But let's get to the code now. We operate on config files that you see here on the side. So all the parameters are here on the side. The main script is enough for you to understand what's happening, how the training functions. And I'll show you how easy it is. Like with original Dreamer, you see main.py and it's like, what is even happening? You see my code, you can just go line by line and understand what's happening. So I'll hope you appreciate it. So let's begin. What happens when you run this code? This happens. So this just runs out of the box. This is a classic, if you don't know this is a classic way to just parse the arguments from the command line. I don't really use them, but they might appear in the future. I might add more parameters here, but for now it's not necessary. I just have one config, that's the default, so I don't have to pass it even. I just run the script and it works. So I pass the arguments with one string for now, the config name. I have one config, so this just executes the main script with this config. So we start here. This is the loop. I mean, you already saw that we print the environment properties. That's from here. You can see the properties for later. Channels, height, width, action size, action boundaries. This is important for continuous values because they actually differ. I mean, steering can go from minus to plus. This is gas from 0 to 1 and brake from 0 to 1. But that's for the future. I don't know why I mentioned it, but it's too late now. I mentioned it. So let's start with the script. We have the config, how it's loaded. I mean, I'm not sure in what level of abstraction to speak. I'm just trying to tell you what comes to my mind to give you a feel for it. But okay, let's go with it. We load the config. We load the YAML file, this file. as a Python dictionary that we convert to attrdict, which means that we can we can index the Python dictionary with attributes. So for example, when we have the config variable config, to get the seed, because this is the base level of this config, we can just go config.seed. Config.seed. Where is it? Somewhere here. Config.seed. And then to get batch size, we go config.dreamer.batch size. Like this. And it's very a clean way to work with it. Then we seed everything. I mean, that's obviously has to be done. We want to eliminate the effect of randomness. We want the runs to be reproducible. So when we make a change, we want to see the effect of this specific change, not just like random seeds, because the runs quite differ out. So like we always seed everything. Remember about this. Then I have I figure out the folders and run names, because here in config you can name your run. For example, I can show you metrics files. Like all this are like full run names with the environment name and my specified name in the config. So like just to distinguish the runs. I mean, I made a lot of them, and that's just like the past 2 months. It doesn't include like a ton of other ones. So yeah, that took me a while. But then we figure out the paths for the folders, because we need to have the folders created that are here in the config below. The names: metrics, plots, checkpoints, and videos. I automatically create these folders because otherwise you'd get an error, because they have to exist, but I will not like include in the repo the videos because these are my local files. So I do this. I ensure that the folders exist with this function. You can read the details, right? I think I will get into like this is so simple that it's not crucial to understanding the algorithm. I'm just like giving you the background of like how do I work with it and what's happening. So that's that. I think that should be pretty clear. And and these are called bases, not file name, but file name base, because we'll have many checkpoints and many video file names. I just append, like later on, I'll append the suffix to them. So checkpoints have the run name plus 2k, 4k, 8k, 10k, stuff like this. But okay, I think I'm talking too much. I think I'm giving you too much detail. What do you think? Let's go further. Then I create the environments. This is a funny way to create environments. Like nobody does it like this. That we have 2 environments, okay? Think about this. Because I want to create the videos to inspect every checkpoint, how it behaves, what's happening. I have all the checkpoints and videos for every checkpoint to see what's happening. And to record videos, I need to have the render mode passed of RGB array to the environment. I mean, if you didn't work with Gymnasium, these are just industry standard environments for reinforcement learning, originally developed by OpenAI back in the day when they were doing ML. Yeah, so anyway, like you should probably know this. Like I will not explain it here because that's like super basic to figure out how to work with it. But okay, I was saying that I have 2 environments. I need to pass the render mode to record videos, but there's a chance, like I cannot find definite information on the internet, but I believe that's what ChatGPT told me, that like they could skip some internal logic if I will not have the render mode, because default render mode is none. So I cannot even render the frames. But I want to render the frames for videos, but I record videos only on a small minority of the runs. So I was just like, okay, hopefully, I mean, let's do it like this. I created the base environment on which I train, so it's like as fast as possible because I train. I don't need to render the frames. Then I have a special environment for evaluation, for recording the videos. And I just hope that it's really quicker in this way, because otherwise it looks stupid. I've never seen anyone do it like this. It's all very weird, very crude. It's like a guerrilla tactic of an amateur. So I don't know. I do it like this for now. It might change if you if you watch it in the future and you see that it's gone. Then it was stupid. Then I get the environment properties in one line nicely. I will not elaborate. We just call them the Gymnasium API to get the properties that you saw here, right? These are the properties that we pass. In the future, we'll need more. We'll need to have. I mean, for now, I only have continuous action space. But in the future, I'll be probably passing, the type of the action space. I'll support like normal non-image observations. So this will change, but it's like this anyway for now. Then we have the Dreamer. We instantiate the Dreamer class, and then we pass the config Dreamer. Remember? So what Dreamer will have access to, like this level of the config will be its base level. Like it will just call self.config.batch size. So it's neatly organized. Nobody does it like this. I actually organize it very well. In the Dreamer, you can see that every subclass, every neural net has its specific config nicely passed. They don't like take internally what they need from the config. They just have what I want them to have. So in code, they will have only these four. That's nice. I like it. So that's config. If we want to resume, if the flag is true here, if we resume true, then it will load the checkpoint specified here. This specifies the suffix that we want to create. I mean that we want to take with a specified run name. Right. Okay. Quick break because my throat's gonna go crazy. Then we have environment interaction, and this function is my equivalent of like a on a high level. So the internal logic is hidden underneath the function, but this is my function to gather new data. Remember, the Dreamer gathers data, trains the world model on this data, and trains the behavior on the world model. Okay, so this will be the function to gather new data, to play an episode, specified number of episodes actually, but it's usually one, except the warm-up, because this is this is the training loop. This is before the training loop. We play like episodes before start. So these are like warm-up episodes before we start training to have some data for the diversity. We like diversity, yeah. And then we have the training loop that's organized in two loops because we train the model here. Here we gather new data. And this ratio, this replay ratio, determines how often we train versus gather new data. Like I can straight up just, for now it's 100. That's what they used in original Dreamer. I can just straight up increase it to increase the effectiveness of like sample efficiency. So we can learn more on the same number of data. Yes. So this is our training loop. Here we could quickly figure out how many iterations we have to make of this based on how many gradient steps we want and what's the replay ratio. So we sample data here. We train the world model with the data, right? We get the initial states. I mean, we return metrics. That's for debugging. That's only for me. And initial states. So the full states that will kickstart the rollout process, and then we change the behavior using the initial states and the world model, and we return the metrics and increase the number of gradient steps because we want to track them, right, for later. This executes if I mean, if the number of gradient steps happens to be divisible by the checkpoint interval, and we want to save checkpoints, then we save a checkpoint. And every checkpoint is figuring out the suffix or suffix. I think it's suffix. I divide the gradient steps by 1,000 and add the k for shorter, for shorter names, because this will be like too long. And you'll specify the suffix here, remember, with the checkpoint to load. Then we save the checkpoint of specified name of the base plus the suffix. Then we evaluate the score with our weird evaluation environment, and we save the video. Right? And this, in the evaluation mode, we don't gather new data. So this is purely for evaluation. This is not for gathering data, but we return the score that we got and we print it on the console just to track the process of the current stage of the process. So that's the loop that runs 100 times. I mean, here this is unnecessary. I already changed it I have it in my changes that these two are unnecessary. It will be like this, but for now I cannot really do it because I already committed it. I cannot make changes, so I'll push it later, but the functionality is the same, so it's fine. And then after we trained for 100 steps, we gather new data with this function. And then if you want to save the metrics, if the flag is here true, it's true by default, we get the base info about the environment steps, gradient steps, recent score from this function, and then we connect the metrics with the word model metrics and actor critic metrics, and then we save it to the CSV file. I can show you the file. Let's see something good. That's the file. A big file of just helpful metrics. KL loss, actor loss, critic loss, advantages. Just for me to see what's happening. And like with this file, I can do anything, right? I can open it in Excel and make some graphs, make something. But then we also plot the metrics. So I have a special function that creates an HTML plot from these metrics for me to inspect and play around. I can show you the plot. This is the plot. I mean, the scale is messed up. So if we turn off this and this, we see some traces. We want to see only total reward. This is the run. This is what you saw on GitHub. Really nice training. Here, I believe it's overtrained. Maybe it would get up with time, but I don't know. I'm not convinced. Like still like 900 average reward, because this is averaged over 10 steps, 10 episodes. So over 900 rewards is like max on this environment. So like this is solved. Like here it was already solved and solved here. So we don't need to train it more. This is just overtrained, I believe. So overall, really good run. And that's it. That's the main script, right? Like I told you, like this is the core. Gather data, train the word model, train behavior. And it's very clear how you would proceed. Like if you want to inspect how the word model trains, just follow the function and see what's happening. Like it's obvious. Like you have the top, the main script, and then you can branch out. With all these other all the other original Dreamer, I open the script and I'm just like, dude, no idea. I cannot tell you what's happening there. So this is nice. I'm really proud of this. As you see, like if you really want to understand it, because that's how I used to learn reinforcement learning, that like I started by taking someone else's code and just deleting everything that's unnecessary for me. Not like unnecessary overall, but like in the moment for learning. Like every line matters. Like the metrics. Why would I need the metrics? When I'm trying to understand the algorithm, no metrics. Not this. I don't need checkpoints even. delete the checkpoints. What's happening here? I don't need the files. I don't need 0 files. I don't need this. I don't need this. I need this. I mean, okay, that's a bit too much, but you get the point. Like, it's clear what's happening, I hope. Nice. Now we can proceed with more details. I think we'll get to the word model training, then behavior training, then the neural networks. Just like a quick overview of what's happening, so you know, like, I will not explain to you everything. Like, I want you to know what's happening. So if you want to understand something, like, you know what you have to research. Alrighty, word model training. We'll go through this, but for educational purposes, I took the whole function out into the Jupyter notebook. So everything's the same except the self keyword has been exchanged for Dreamer. So it works, but you know that we're analyzing this, which is in Jupyter notebook. So our main loop passes data to us, the sample data, right? We're getting the data, and then we process it. So we first pass the observations from the buffer, reshape them this way, then we pass it to the encoder, reshape it back. Why is it done this way? First of all, data observation. Okay, of course I had to run it first. Okay, so this is the observations from the buffer. This is batch size, batch length, and the observations, right? 3 channels, 64 by 64, sequences of 64 time steps, and 32 sequences like this that are specified in the config. So it can be complicated, but pretty much we do this reshaping trick because encoder expects at most 4-dimensional input, because it knows that there are 3 channels consisting of the image consisting of three dimensions here, but it has only it has only capacity for the batch dimension, and we have 2 additional dimensions. So we pretty much collapse this together. So let's see how that goes. So I do it like this, dot shape. We collapse these 2 dimensions together. So this number is 32 times 64. Okay, then we pass it to the encoder. Shape to get this. So we have the same batch size times batch length, but the 3 last dimensions are just collapsed into this representation, this encoded observation, and this size is specified in the config, right? Encoded ob size. Okay, this is the size, and then we reshape it back because we want to have it in the original form. So we reshaped it back 32, 64, 1024. This is the trick to just pass the whole thing with batch size and batch length through the encoder. Okay, I hope that's somewhat clear. So we have the encoded observations. Then we initialize recurrent state and later state. And I have to immediately apologize because that's not what I showed in the diagram. Because this went through like many reworks. I didn't check. I forgot to check. That's the diagram I created earlier. Stuff happened. My mistake. That this is the fixed diagram. So we don't initialize this recurrent state with zeros. We initialize recurrent state here and latent state. We take our first action from the buffer to just get the new recurrent state. And now we create the rollout, meaning that we don't use like the 0th observation here. So we encode it here, we encode all the observations, but because of the setup, we cannot ignore the 0th observation. So that's my bad. I believe it can be because I had some problems, like I will not get into detail why I had to rework it like this, but I believe I could fix this in the future. So this might change, but I'm sorry, the diagram didn't match my code in the previous version. But that's the only change. The rest stays. So we initialize the recurrent state and latent state with zeros of the specific sizes, and this length of that action is just our batch size. I don't know why is it like this. I believe that it's because it's shorter this way, but it's less clear, so I'll change it in the future commit. But it should be like Dreamer, like self in the real code, Dreamer config.batch size. Like it'll be longer. I don't like the length of this line, but it's still fine. It's still fine. So this is just batch size. We initialize them, but we don't have the sequence length here. I bet like some people might ask about this, because this recurrent state represents a singular time step. Then we'll stack them together and have the batches and sequences. But this for now is just one time step, so it only has the batch size dimension, not batch length. Then we initialize the lists and we make our rollout that we all know and love. Recurrent state passed with these initialized values and the action, right? This. We take recurrent state and pass it to the prior net. We have prior here, this is prior, so the output of this net, but we don't use it in word model training. So we just need the logits for further training. We take posterior logits, right? We only use the posterior, only posterior. And we pass to the posterior concatenated recurrent state and encoded observation. I like it this way because many people, like pretty much everyone I checked, is concatenating, like it's passing these two, or like universally, if there are like two things that have to connect in the net, they pass the two things and then connect them internally in the net. But I like to treat it as one entity that I connect, and posterior net just gets one input of specified size. That's also why I connect the recurrent state and latent state into full state. Like, I feel like it's easier to work this way. All right, then we append to all these lists our 4 outputs that we passed. And then we change the previous recurrent state and previous latent state. Then we stack them on the sequence length dimension, on the like time step dimension, because by default it's 0, so it would stack them on the first dimension, but that's not what we want. So we pass it and we create the full states from recurrent states and posteriors here. We just concatenate it. So we have one thing, one full state that we can pass to all the nets. So now it's time to train the nets. Decoder, we pass to decoder just full states. That's it. But we do the reshaping trick because we also have to pass the 5-dimensional input, but the decoder only takes 4 dimensionals. So we do it like this, and we treat the decoder output as means of normal distributions of deviation 1. That's how it's done. We still just maximize the probability of returning what we observed in the buffer, right? That's the loss that we all know and love, minus log prob that we return this. And that's independent because like every distribution that comes from here is independent. They shouldn't be influencing each other in any way. So then we have the reward distribution, predict rewards from full states, but this time reward predictor already returns the distribution that we can directly call log prob on, and we just maximize the probability that we will return the rewards from like ignoring the 0th reward, right? Because we don't have the full state for it, and that's done. And then this is a bit complicated. How do I explain it to you? Let's go to the paper. What is mastering diverse domains through while models. So, I mean, I probably will not explain all of this to you, but how we train the two nets, I don't know why they distinguish it into two separate losses. I just add them together because it's just one KL loss for me. But what they want to do is they want to minimize the KL divergence. I mean, it's like you have to read about this. Long story short, we just like KL divergence is a measure of how two different distributions differ from each other. Okay, so we just take the raw logits, we create category called distributions from it, from them, and then we want to match them together. And how they do it, I'm not fully like I wouldn't be able to like fully explain it to you, but they calculate the same thing. That's like these two losses here. The equations are the same, like the values will be the same, but the dynamics loss stops the gradient here on the posterior like output, and we want to minimize the difference here, but only like into the prior will flow the gradients. And here, representation loss is the same thing, but we stop the gradients here. And they have different weights. Like what weights do I have? It's 1 for the prior, for this dynamics, and 0.1 for the second one. So we'll be changing the prior more to match the posterior, but posterior is also like slightly matching the prior. It's a bit complicated. I'm not fully sure why it's done like this, but that's how it's done. And we also max the whole thing with 3 nats of 1. And they do it so if these two distributions like match each other decently well, that the loss is like smaller than 1, then we just max it, meaning that no gradients will flow because it's a constant, right? There's 0 gradients. We just focus on different nets. We prioritize them. So that's how I do it. I create 4 distributions with logits from prior and detached, from posterior and detached. So I have 4 of these. Then I calculate the KL divergence. I create the tensor with the 3 nats that I max with prior loss and posterior loss. I apply the weights, I add them together, mean, and that's my K loss. Okay, I mean, that's as much detail as I will give you right now because, you know, the topics here are a bit tough. So we have the reconstruction loss, the reward loss, the K loss, then we add them all together, right? They calculate it separately like this. I mean, they have like the weird naming convention, and then they add them all together here. It's pretty much the same thing. I just like slightly reframe it. So that's the word model loss. And if we use the continuation prediction, that is not tested in my implementation, so I haven't used it before. But I cited it should work pretty well. But if we use it, and the flag is what here, if we set it to true, it will add to the word model loss the continue predictor loss. From full states, calculate the loss of real data. We know the drill with this. Then we step the optimizer, and I get my metrics. I mean, I can explain the K loss shift for graphing because of this maxes here and the weights here, the K loss cannot go below 1.1, so it's always shifted. And I don't like the shift for my plots and debugging, so I just shift the word model loss and K loss, so it's like back to 0, but it doesn't change the numerical values here in the actual training loop. And that's it. We return the initial states, so the full states from here, but we reshape them because they like the sequences, the batch size and batch length don't matter anymore. We don't distinguish them. We just have all the full states that we of course detach. We don't want any gradients there, just in case. And we return the metrics, right? This was our Jupyter notebook. Let's delete this. So this is the actual function, and we just return this stuff. Hopefully you understood something at least, okay? Please say yes, please say yes. Then we get to the behavior training. So the only input here is initial states that we call full state here, like this, because this is the like one time step only that we get here. Like I wanted to pass only singular thing for easier, cleaner main function, and just a nice framing. I like the framing of having like passing only one thing, but unfortunately, for practical reasons, I have to split it into recurrent state and latent state, because that's how recurrent state works. That I have it separately here. I don't contain like one package because I'd have to split it anyway, because recurrent state is being passed to the recurrent network, but these like other inputs are being processed by just linear fully connected network. So unfortunately I have to split it, but the rest works as we remember. From this initial state, we created a rollout of imagination horizon steps. We just get the action. I mean, let's get to the diagram that's slightly updated. That this full state from word model training is being treated as the zeroth full state and is being passed to the actor and recurrent model, right? This full state is to the actor and recurrent model. From this we get the prior, right? We concatenate it to have the full states before even appending. We append them, we stack them. And remember that when we operate on the tensors, we would ignore the zeroth log prob like this. We take the whole batch and then ignore the zeroth time step, okay? But here, because I do it here, I don't even stack it, and this is still a list in this moment. That's why I index it like this. So on the tensor, it's the second dimension, but on the list is one dimensional, right? So don't mix this up. But okay, then we pass the full states to the reward predictor, and remember that reward predictor returns the distribution. So this just takes the mean of the distribution to get the actual rewards. So like the reward that has the highest probability according to the reward predictor, according to this distribution that it returns. And we also ignore the last time step, is because we will not use this reward. Remember this, we need the rewards, but for the last evaluation we don't need it, because we have to have the bootstrap. So we don't need the last reward, so I ignore it, but we need all the values from all the full states. And we also take the mean, because that's what critic returns, the distribution. And then we get the continuous that already incorporate the discount. So if you're looking for like the gamma factor, where's the discount? So this is how we would pass the full state to the continue predictor, but we don't use it right now. I have the tensor of just discount values, thinking that continue is 1. Okay, and then we pass it to lambda values that we already went over. That it's nicely going backwards on the equation. So we have the lambda values, then we pass them to value moments, which is an interesting class here that I have. And this is the exponential moving average trick from the paper. That we just estimate the range of values based on 95th and 5th percentile with 0.99 decay rate. So this is all this. We just estimate the scale of it to return the inverse scale that we can scale the lambda values and values with, okay? And we have one less lambda value, one fewer compared to values. So we ignore the last value, because on the last value, if I didn't have it like this, on the last value they would match, right? They would exactly match. So it would be kind of pointless here. So I just ignore the time step. And then we have the actor loss. Finally, we maximize the probability of disadvantages according to disadvantages. So if advantage is positive, we increase the probability. We want to increase the probability of taking that action. This is of course detached because actor is because we have a stop gradient here, right? And this is the entropy term. This is the coefficient times entropy. Coefficient times entropy. And we step the optimizer. Then we optimize the critic on full states. That returns the distribution. We maximize the probability of matching the lambda value. We step the optimizer, we get the metrics. Wow, we got to this. Alrighty, I mean, okay, I didn't use the Jupyter notebook as much as I wanted to, but we got to this. These are these functions. And that's how it trains. Get the data, train the warble, train the behavior. Is that somewhat clear, my dear students? Any questions? Let me know. And we move on to networks. Yay. Okay, let's get through the neural networks, our building blocks of our Dreamer. So recurrent model takes in recurrent state, latent states, and action. This is an exception that it's all separate because we have to process the parts in different ways. We want to pass all these inputs to the recurrent network to get the new recurrent state. But for that, we take the other inputs, not recurrent ones, concatenate them together, latent states and action, pass them through the linear layer. One layer, could be more, we're using only one. Then we pass it to activation, specified in the config, right? Here's the config. Also, the size is specified here for the linear network. And then we pass all these processed latent state and action alongside recurrent state to our recurrent network. It looks maybe a little bit convoluted, that it's just in one line, but I feel like it's very clear. I mean, if you study recurrent networks, this should be fairly simple. I actually have had to learn recurrent networks. Wait, where's my profile? I have my recurrent neural network study. This is neural network by hand in NumPy, then the same one in PyTorch. So if you don't know how it works, I recommend you check it out. Why not? But this is fairly simple. Like, based on this input and previous recurrent state, we get the new recurrent state. Next up, we have our prior net and posterior net, which are pretty much the same nets, except they have different input, right? Like, okay, actually, the code looks the same here exactly, because we just have input size, we process the input size. Actually, so yeah, this is the same. But here in the initialization, the input sizes passed are different, because for prior net, we have input size, recurrent size, but for posterior net, we have input size of recurrent size plus encoded size, right? But the rest is the same. So I feel like it's pretty neat that I organized like this, that I don't have to change the internals, but it's like on the outside, it's visible what differs here. So these are the nets. Let's go to the prior net. And we pretty much create the latent size just to have it neatly accessible, then multiply two values to have the total size of the output. Then we have our multi-layer perceptron. Actually, I should just call it network. Why is it like this? But okay, it's fine. I'll leave it for now, so you don't have any differences between the Comet and this tutorial. But yeah, this is just MLP. From this function, that creates the sequential network. That's quite easy to read without getting into this function. It just appends the layers. We have the input size. Then we pass the list with specified sizes of hidden layers. And the size of the list determines how many layers there are. So that's quite simple. We just have like list of one element of specified hidden size multiplied by the number of layers that we specify in the configs. So, I mean, this should be very simple. That's output, that's activation. Okay, so that's just like a simple multi-layer perception. So in this case, our output size is just 16 by 16, right? We pass in the logits through the network. We arrange them in this matrix to have 16 distributions from that. Softmax. This trick is applying mixing uniform distribution with what the network outputs, and it's a trick from the paper. Oh, here it is. So they observed spikes in K loss, and to prevent, they just mix in 1% of uniform distribution, which is like, does it even change the performance? Like, why do we need to prevent the spikes? Like, I observed the spikes actually without the unimix, but I don't know why they do it. I just do it because that's what they wrote in the paper. So, I mean, as you trace in what's happening here, we create ones divided by number of classes to like evenly distribute the probabilities. We mix it, the probabilities, with the uniform distribution, and new logits are passed to our distribution to create the distributions of like one hot output for each of the rows of this representation, right? I hope that's clear. I mean, for clarity, if you want to study it, you can delete all of these, right? The uniform mix doesn't really matter. We just output logits here. Like, this is the whole function. We create the distributions, sample from it with a reparameterization trick. So I sample from it so the gradients can flow to it. And then we, for the sample, for the output, we collapse the last two dimensions because we don't need to have them arranged in the matrix, but we keep the logits for further processing. And I mean, that should be pretty simple if you analyze it further. Reward model, simple neural network, very, very simple, with two outputs of mean and log standard deviation. Then reward model with only two outputs. So we pass the input through the network, split it in two along the last dimension to get our mean and log standard deviation that we exponentiate to get the standard deviation. And then we create the normal distribution, right? So reward model, as you remember, returns the distribution that we just sample log prop from. And pretty much the same network is used for the critic. And this works fantastic, right? We just assume that the distribution of critic, of like values and rewards is normal distribution. But many, like not many, but environments can be more complex. They might have multiple modes of rewards, for example. Like it's not just Gaussian distribution. Maybe there are like two peaks. Maybe the reality is really complex. And to model this in actual original Dreamer, they use categories. They use like bins that represent different ranges of values, and they represent continuous values with these discrete bins that can model more complex distributions and two hot laws, and like this is too hard. I will not explain it right now. I'm studying it currently, but just know that this doesn't quite match the Dreamer. This works fantastic, but like they use the two hot laws. These are the bins from -20 to 20 in log scale. So then that's like exponentiated later on. But all you have to know is that we model it as normal distribution because that's the most popular like distribution of the rewards. It works fantastic. But if you wanted to create a truly universal algorithm, like they had to use the two hot laws that I don't currently support. I'm working on it. I implemented it, but it doesn't like it doesn't quite work. Like I wrote everything correctly and it doesn't work yet. So so I'm working on it, but on this version we have only simple normal distribution, and this detail is missing that was lost. So so that's that. Then we have the continue model, simple neural network, one output only with Bernoulli distribution. And Bernoulli distribution is just either 0 or 1 at certain probabilities. Then we have the encoder, and encoder, like for now I only support image observations. For numerical observations, it will be just a simple multi-layer perceptron, but for image observations, this is just a convolutional neural network. If you don't know this, we just take the image inputs, we create, like we compress it, we draw like infer features from it, and then at the end I have linear network to output the specified size. So the output is standardized to whatever I want. And the encoder does the exact opposite, because it has to reconstruct what encoder encoded. Then we have the actor as the only thing left. And I don't think I will explain the whole thing. I can tell you that I made this actor based on CleanRL, one of the best libraries for simple reinforcement learning algorithms. And I studied this actor from SAC Continuous. So this is pretty much taken from this. And what it does is, I mean, how they did it is they nicely enforce the bounds of actions. So I needed this, so it performs nicely. For example, this is a correction term because of the rescaling to the log probability. I also take the entropy. And this operation, for example, is a simple linear mapping from input range of values to desired range of values that we specify here. So you can check out the formula for this. I pulled it up quickly from ChatGPT. This is the formula. This is D minus C, this max minus desired max minus desired min, divided by input range, which is 1 minus minus 1, so it's 2. We just divide by 2. This is our input, tanged, of course, because we want to have it in the range of minus 1 to 1. Then this is the minus C, but C is minus 1, so we add plus 1, and then we add the C here, right? So you can get into the math, you can study it. I'm just telling you that this nicely keeps the bounds of this of actions specified here. Then they adjust the normal distribution for the correction factor. This is just fancy math that works. All right, I think that's enough, because I mean, if I had to explain in detail all this stuff, I mean, this video would have like what, 4 hours more, and I'm not even nearly as prepared as I'd like to. So let's finish here. That's all the theory we need. Hopefully you learned something. That's everything we need to understand. I mean, in plans I had to show you how to use the whole script, but I bet like by watching all this all the content so far, you know pretty much everything about it. Like pretty much don't really change this ever. That's why it's at the end. You could manipulate this to check to modify the sizes, maybe run bigger models, maybe smaller models, and see what's the performance like. Here are some parameters, but this is pretty much the range where you'll be operating on mostly. This run would be for 60,000 gradient steps with this replay ratio, saving metrics, saving checkpoints every 2000 iterations. We don't resume, meaning that we start from scratch. We randomize the models and train them. And so this doesn't matter. This doesn't apply to us. But if I wanted to resume something, I can resume it. For example, let's resume 94K of tanged no clamping. And resume true. Will this work? Will this throw an error? it works. Oh, this is some warning from PyTorch, so it loaded the checkpoint and it just runs and trains. And we have the metrics file already, but this metrics file, I mean, where's the thing? Like, we'll just get appended new rows to this. And that's it. That's the Dreamer. Things will change. We can open the README, we can read the README, or we can render it maybe. I have the to-do section here, so definitely I have to work on these things. These are things to keep in mind. The to hot loss what happened? To hot loss. What is going on? I click. Oh, I really cannot double click it. Oh my goodness. Okay, so the to hot loss, definitely I mentioned it. I have to work on it, and then we'll expand. I mean, the priority will be to expand to other environments and support different types of observations, different types of actions, because we don't have discrete actions. We only support continuous ones for now. And for different kinds of observations, we'll need another encoder and decoder that handles different types of the input. Then this is interesting. I'll look into this. Soft actor critic. I know how to do it. It's just like it would be ugly if I did it. Soft actor critic is a technique to use two critics. So like optimize. We have the critic. We optimize the critic, but it's let's say very jittery, and for as a target for actor, we use a critic that lags behind the first critic, so it's more stable. It's a bit slower, but it's more stable. So we have the target to the for the actor is more stable, and it supposedly improves the performance. But in order to do that, I'll have to calculate the lambda values again, pass to the model again. I have to remodel something. I was just like, I don't think it will improve the performance enough to like justify it for now, but we'll look into this. I'll test the continue prediction and remake the buffer because it's currently taken directly from, I mean, I slightly reformatted it, but I should remodel it completely. So, you know, there are plans, things will change. I definitely need a break from this because that's all I've been working on, like, not all, but like the main thing I've been working on for the past month. So I'm so sick of it, sick of everything. I don't want to see it. I hope that you'll make some use of it. I posted this on Reddit already, my repo, and people liked it. So I'm really happy because I'm making an actual contribution to the to the community. Like I did something and it helps people because Dreamer code was terrible to read, just almost impossible to learn. Like rarely anybody has that much like time and effort to dedicate to understand the Dreamer. So I did the work, you guys study it, do something, start my repo. Where's my repo? Start my repo, fork it. I already have one fork. Someone wants to do something with it, so hopefully I'll take some break. I'll continue to work on it and we'll do something nice with it, so it can only get better from now on. People suggested on Reddit that I add the algorithm to some libraries like TorchRL, even CleanRL. One of my favorite RL libraries don't have the algorithm, so I mean, either hopefully I will contribute directly to these libraries or indirectly, that people just take the code, study it, and do something from it. So I'm happy, I feel accomplished. There's still some work to be done, but for now, thanks for watching. Also, I'll have to update the graph in my, because the graph from the comet, yeah, it has the mistake. It's fine. I just hope that you learned something today. If you watched the whole thing, do kindly let me know. I'm curious if anyone watched the whole thing because I don't even know how long the video is, but there's so much content. There's no way that everything is perfect. It was hard. I don't know how I feel about it, but the job is done. You learned something hopefully, and it's time for me to go. I'll take a break from the Dreamer, then work on it further. Oh, I need to move a bit. I think I'll go on a walk. Alrighty. Thanks for watching.